You cannot die, not in the way you think. There is a version of you reading these words who will never, under any interpretation of physics currently on the table, experience the moment of their own death. This isn't a comfort offered by religion, and it isn't a metaphor. It is a mathematical consequence of quantum mechanics, taken seriously, and serious physicists argue about it at conferences, not in philosophy clubs. The argument is this: if the equations are right, and if one particular interpretation of those equations is correct, then the subjective experience of dying is simply not available to you. You will always, from your own perspective, find yourself on the other side of it. Now, that claim sounds insane, and the right response to it is not to nod politely, but to ask exactly what kind of physics produces a conclusion like that. Because the answer involves one of the deepest, most unresolved problems in all of science. A problem that has split the physics community for 100 years, that drove Einstein to the edge of frustration, that a 27-year-old graduate student once thought he had solved at a late-night party over glasses of sherry, and that may, or may not, change everything you think you know about what reality is. The problem has a name. It's called the measurement problem. And to understand quantum immortality, you first have to understand why this problem has kept physicists up at night since the 1920s. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions have been confirmed to more decimal places than any other framework humans have ever built. Physicists use it to design computer chips, lasers, MRI scanners. It works. The uncomfortable thing is that nobody fully agrees on what it means. At the heart of the theory is something called the wave function. Think of it this way. In classical physics, the physics of Newton, the physics of billiard balls and falling apples, every object has a definite state at every moment. A ball is either here or there. It's moving left or moving right. You can describe it completely. That's the picture most of us carry around when we think about physical reality. Quantum mechanics says that picture is wrong, or at least radically incomplete. At the level of elementary particles, electrons, photons, the fundamental building blocks of matter, objects do not have definite states before they are measured. An electron doesn't have a position until something interacts with it. It doesn't have a spin direction until you check. Before the measurement, the best description physics can offer isn't "the electron is here." It's a mathematical object called the wave function, which assigns a probability to every possible outcome simultaneously. The electron is, in some precise mathematical sense, in all of those states at once. This is called superposition. The wave function isn't a metaphor. It's not physicist shorthand for "we don't know where the electron is yet." It describes a genuine physical reality, a reality in which the electron literally occupies multiple possible states at the same time. The evidence for this is not philosophical. It shows up in experiments. The most famous one is the double-slit experiment. Fire a single electron at a barrier with two narrow openings, and on the other side, you'll eventually build up a pattern that looks exactly like waves interfering with each other, as if the electron passed through both slits simultaneously and interfered with itself. This pattern only appears when you don't check which slit the electron went through. The moment you place a detector at one of the slits to see which path the electron takes, the interference pattern disappears. You get two bands instead of the wave pattern. The act of observation, the interaction with the measuring device, changes the outcome. Not because the detector disturbs the electron physically in any simple mechanical sense, but because the observation itself does something fundamental to the quantum state. That something is what physicists call collapse. The wave function, This spread out, many possibilities at once mathematical object suddenly snaps to a single outcome the moment a measurement happens. Before, probabilities spread across many states, like a coin spinning in the air, genuinely neither heads nor tails. After, one definite result. Heads. The coin has landed. The question that has tortured physics ever since is this: what actually causes that collapse? What counts as a measurement? Where exactly is the line between the quantum world, where superposition exists, and the classical world, where things have definite states? And, most unsettling of all, does the wave function actually collapse, or does something else entirely happen? That last question is the one that cracks the door open to everything that follows. In 1935, a physicist named Erwin Schrödinger decided to demonstrate how absurd the measurement problem really was. He'd helped create the mathematical machinery of quantum mechanics himself. The wave function is literally named after him, the Schrödinger equation. But the interpretation being pushed by the Copenhagen school, led by Niels Bohr and Werner Heisenberg, struck him as genuinely, deeply wrong. So he built a thought experiment designed to make the absurdity impossible to ignore. The setup is almost theatrical in its simplicity. A cat is sealed inside a steel chamber. Inside the chamber with the cat is a device containing a tiny radioactive substance, so small that over the course of an hour, there is exactly a 50% probability that one atom will decay. Decay is a quantum event. It happens or it doesn't, and before it's observed, quantum mechanics says the atom exists in superposition. It has both decayed and not decayed simultaneously. Now here's where Schrödinger made his point. The device is rigged so that if the atom decays, it triggers a Geiger counter, which activates a mechanism that shatters a vial of poison, killing the cat. If the atom doesn't decay, the cat lives. Close the box. Wait an hour. According to the Copenhagen interpretation, according to the official answer that had been codified as the standard understanding of quantum mechanics, the atom is genuinely in superposition until measured. Not, we don't know if it decayed. Genuinely both decayed and not decayed. But if the atom is in superposition, and the cat's fate is mechanically linked to the atom, then the cat must also be in superposition. The cat is, in the language of quantum mechanics, simultaneously alive and dead until someone opens the box and looks. Schrödinger called this quite ridiculous. He wasn't proposing a genuine experiment. He was holding up a mirror to the theory and saying, "Look at what you're claiming. You're claiming that an animal, a living, breathing, biological system made of trillions of atoms, exists in an undefined state until a conscious observer interacts with it. You're claiming that the act of opening a box is what decides whether the cat lived or died, not whatever actually happened inside. You're saying that reality itself is suspended, hovering in ambiguity, until an observer arrives to collapse it into existence. And the deeply uncomfortable thing is that if you accept the Copenhagen interpretation, if you take it at face value, Schrödinger was right to call it ridiculous, and yet the mathematics forces you there anyway. The cat is in superposition. That's what the equations say. Saying otherwise requires adding something extra to the theory, something that isn't in the mathematics itself, a rule that says collapse happens when an observer looks. But what is an observer? Is it a human, a camera, a Geiger counter, a thermometer? Where exactly does the quantum world end and the classical world begin? Nobody has a clean answer. That's the point. That has always been the point. The Copenhagen interpretation, Assembled primarily through the work of Niels Bohr and Werner Heisenberg in the 1920s, sharpened and promoted through the following decades, was the physics community's official answer to the measurement problem. And for most of the 20th century, it was the only answer most physicists were willing to entertain. Not because it was satisfying, but because it worked, and because Bohr's personal authority and the momentum of success gave it a near unassailable position. The core claim of Copenhagen is this: the wave function is not a description of physical reality. It is a calculation tool, a mathematical object that encodes probabilities. When a measurement is made, the wave function collapses, not because something physical happens to the quantum system, but because we have updated our information about it. Reality, in this view, is fundamentally probabilistic. There are no hidden variables ticking away underneath, no deeper level of description that would restore determinism. The randomness is irreducible. When you measure the spin of an electron and get up, there was no pre-existing fact about which way it was going to go. It simply wasn't determined until the moment of measurement. That's not a limitation of our knowledge. That's the way the universe actually is. Heisenberg put it with characteristic bluntness. The path of a particle, he said, only comes into existence when we observe it. Before observation, talking about where the particle was is meaningless. Not because we don't know, but because there was no fact of the matter to be known. Albert Einstein hated this. Einstein had contributed enormously to quantum theory in its early years. His explanation of the photoelectric effect, which earned him the Nobel Prize, was a foundational quantum result. He understood the mathematics. His objection wasn't ignorance. It was something much deeper. A conviction that physics should describe an objective reality that exists independently of any observer. God does not play dice, he said, in a phrase that became one of the most quoted objections in the history of science. He wrote this first in a letter to Max Born in 1926, and he kept saying it in various forms for the rest of his life. In 1935, Einstein, together with two colleagues, published a thought experiment, known today as the EPR paradox, after their initials, arguing that quantum mechanics must be incomplete. His reasoning: if quantum mechanics was correct, then two particles that had interacted could influence each other's measured properties instantaneously across any distance. Einstein called this spooky action at a distance, and he was certain it meant the theory was missing something. There had to be hidden variables, he thought, deeper facts about the world that quantum mechanics simply wasn't capturing yet. Restore those, and you'd restore a sensible, deterministic picture of reality. He spent the last 30 years of his life looking for those hidden variables. He didn't find them. Later experiments proved he was wrong about entanglement specifically. The spooky action at a distance turned out to be real, not a sign of incompleteness. But Einstein's resistance to the probabilistic picture pointed at something genuine. The Copenhagen interpretation, for all its practical success, had a philosophical cost. It required you to stop asking certain questions. Where exactly does collapse happen? What constitutes an observation? What is the wave function, really? Bohr's answer essentially was, don't ask. The theory gives you probabilities for experimental outcomes. Use them. The rest is metaphysics. Most physicists, for most of the 20th century, followed that advice. They calculated, they built things, they won Nobel Prizes, and they did not look too hard at the foundations. But in the mid-1950s, at Princeton University, there was a graduate student who had never been taught to stop asking. His name was Hugh Everett III, and he had come to physics by an unusual route. He'd started graduate school in mathematics, drifted into physics when he began taking classes with John Archibald Wheeler, one of the most celebrated theoretical physicists of the era, a man who had supervised the doctoral thesis of Richard Feynman, and found himself obsessed with a question that almost everyone else in the field considered either solved or unanswerable. The question was, what happens to the wave function, really, during a measurement? The idea that would eventually become the many worlds interpretation has a documented origin point. One evening in 1954, Everett later recounted, after a slosh or two of sherry, he and his Princeton classmate Charles Meisner were joined by a visitor named Åge Peterson, an assistant to Niels Bohr himself, in from Copenhagen. The three of them spent the night thinking up what Everett described as ridiculous things about the implications of quantum mechanics. And somewhere in that conversation, a question crystallized that Everett could not let go of. Under Wheeler's guidance, Everett had begun thinking about quantum cosmology, the attempt to describe the entire universe as a quantum system. And here was the problem with Copenhagen. If quantum mechanics applies to everything, then it should apply to the measuring apparatus, and to the observer, and to the entire universe. But Copenhagen explicitly divided the world into two realms, the quantum system being observed, and the classical observer doing the observing. That division was, in Everett's view, not just philosophically unsatisfying, it was incoherent. If everything is made of atoms, and atoms obey quantum mechanics, then observers are quantum systems too. You can't just declare by fiat that the macroscopic world lives by different rules. And if the observer is a quantum system, then the observer and the thing being measured should be described by a single wave function together. Which means during a measurement, the observer and the observed system enter a superposition together. The Copenhagen answer to this, that the wave function collapses when measured, was, in Everett's reading of the mathematics, simply not in the equations. The Schrödinger equation, which governs how wave functions evolve over time, is perfectly smooth and deterministic. It doesn't contain any collapse. That collapse had been bolted on as an additional postulate outside the theory, because without it, the theory seemed to produce impossible results. Everett's insight, his audacious, career-ending, field-dividing insight, was that maybe collapse never actually happens. Maybe the universe just keeps obeying the Schrödinger equation all the time, without exception. His original draft thesis was called Wave Mechanics Without Probability. He submitted it to Wheeler in January of 1956, 137 handwritten pages. In it, he argued that what looks like collapse is not a physical event at all. It is the result of an observer becoming entangled with the quantum system being measured. When a measurement happens, the observer and the system enter a superposition together, and within each branch of that superposition, each copy of the observer sees exactly one definite outcome. Reality branched. Every possible outcome happened, in different branches, all equally real. In a footnote, Everett wrote a line that is almost alarming in its calm. From the viewpoint of the theory, all elements of a superposition, all branches, are actual, none any more real than the rest. Wheeler loved the mathematics. Wheeler was also terrified of Bohr. John Wheeler was not a timid man. He was the physicist who coined the term black hole. He had been Bohr's student and Feynman's advisor, and he occupied a position of enormous influence in American physics. But he was caught. He could see that Everett's formalism was, mathematically, extraordinarily clean. He desperately wanted it to work. At the same time, he was convinced that any head-on assault on the Copenhagen interpretation, the intellectual inheritance of Bohr, his mentor, the godfather of quantum mechanics, would be rejected outright and drag both of them down with it. So Wheeler traveled to Copenhagen in the spring of 1956. carrying Everett's thesis, trying to get Bohr to at least engage with it. The attempt went badly. Bohr's colleagues dismissed the work. One of Bohr's closest associates, Leon Rosenfeld, was so contemptuous that he later described Everett in writing as undescribably stupid, and said he could not understand the simplest things in quantum mechanics. The thesis that Rosenfeld was dismissing was among the most sophisticated pieces of foundational physics produced in the decade. When Wheeler returned from Copenhagen, he forced Everett to cut the thesis to a quarter of its original length, stripping out most of the references to splitting worlds, softening the language to make it look like an extension of Copenhagen rather than an attack on it. Everett was not happy, but he complied. And then, because he had already taken a job with the Pentagon's Weapons Systems Evaluation Group before his thesis was even finished, he'd needed to avoid losing his draft deferment and needed income. He left Princeton and never returned to academia. In April 1957, Everett defended his abridged thesis and received his doctorate. A short companion paper by Wheeler was published alongside it in the Reviews of Modern Physics, endorsing the work. Wheeler later wrote privately that Everett was disappointed, perhaps bitter at the non-reaction to his theory, and admitted, "How I wish that I had kept up the sessions with Everett. The questions that he brought up were important." When the paper appeared in print, it slipped into, as Scientific American later wrote, instant obscurity. Everett spent the next years calculating potential mortality rates from nuclear fallout for the Pentagon. He would eventually advise officials in both the Eisenhower and Kennedy administrations on hydrogen bomb targeting and nuclear strategy. The man who had proposed that every quantum event branches the universe into parallel copies was now professionally occupied with calculating how many parallel deaths a single nuclear exchange would produce in this one. There was something grimly fitting about that. In 1959, Wheeler finally persuaded Everett to travel to Copenhagen himself and meet with Bohr directly. Everett described it afterward as doomed from the beginning. Bohr, then 75, refused to seriously engage with the theory. He was the patriarch of an orthodoxy that thousands of physicists were using productively every day. He had no incentive to reconsider. The visit accomplished nothing. Everett said later that it had been hell. He never published another word on quantum mechanics after 1957. But his idea didn't die. It just waited. Because the idea buried in that stripped-down, politically neutered thesis, the idea that Wheeler had helped defang before it could even be published, contained a logical chain that, if you followed it all the way to the end, arrived somewhere completely unexpected. Somewhere that had nothing to do with cats in boxes or spinning electrons. It arrived at the question of what happens to you, specifically, at the moment of your own death. And the answer the mathematics suggested was not the one anyone was looking for. Right now, at this exact moment, you are not one person. Not in the sense of personality or identity, in a literal, physical sense. If the many worlds interpretation is correct, then you are already a vast, branching structure of copies, each one having diverged from the others at the exact moment of the last quantum event that affected any atom in your body. Which means the branching isn't happening occasionally or in dramatic moments, or only when scientists run experiments. It is happening continuously, at a rate that makes any number you could write down meaningless. Every radioactive atom in the universe either decays or doesn't in each moment. Every photon hitting your retina either triggers a photoreceptor or doesn't at the quantum level. Every neuron in your brain either fires or doesn't, based on molecular interactions that are ultimately quantum mechanical. Each of those events is, under the many worlds picture, not a coin that lands on one side. It is a coin that lands on both sides simultaneously, and the universe bifurcates around it. One branch goes left, one branch goes right. Both branches are fully, equally real, and in both of them, there is a complete version of you, with all your memories, all your thoughts, all your continuity of self intact, having no awareness whatsoever of the other branch, because awareness is also a physical process happening inside one specific instance of that branching universe. Put it this way, in the time it takes you to read this single sentence, the number of branches that have spawned from this moment is not 1,000, not 1,000,000, not a number with a name in any human language. The many worlds interpretation does not say the universe splits occasionally. It says the universe never stops splitting, at every level of physical reality, everywhere, always. Everett's formalism doesn't just produce a few extra worlds. It produces an uncountable, ever-multiplying structure of realities, each one complete, each one containing people who are, in every meaningful sense, you, living out a version of this moment that differs from yours by the behavior of particles you will never directly observe. This is not a poetic extrapolation. This is what the mathematics directly implies, if you refuse to add the collapse postulate. If the Schrödinger equation runs without exception, this is what you get. A structure physicists call the universal wave function. A single mathematical object that contains all possible histories of everything, all at once, all equally real, all silently diverging. The question that follows immediately from this is the one that stops people cold. If every possible outcome actually happens somewhere, what does that mean for outcomes involving you? Specifically, what does it mean for the outcome of your death? To press that question into its sharpest possible form, a thought experiment was developed that many physicists considered genuinely irresponsible to think about too carefully. It is called quantum suicide. The setup strips the Schrödinger's cat experiment down to something personal. Replace the cat with a physicist. Put the physicist in front of a device, call it a quantum gun, that uses a genuinely quantum random event as its trigger mechanism. A radioactive source with exactly a 50% probability of decay in the next second. If the atom decays, the gun fires. If it doesn't, the gun clicks harmlessly. The physicist knows all of this. They put the barrel to their own head and pull the trigger. From outside, from the perspective of any observer watching, what happens is straightforward probability. Half the time the gun fires, half the time it doesn't. Over repeated trials, roughly half the physicists in this thought experiment die, and roughly half survive. The outside observer sees this play out exactly as classical statistics would predict. Nothing strange. Now ask what the physicists themselves experiences. Under the Copenhagen interpretation, or under any interpretation that treats death as a straightforward physical outcome, the answer is simple. Either the gun fires and the physicist's experience ends, or it doesn't, and they continue. 50% chance of each. Nothing philosophically unusual. Under many worlds, the answer is different. When the quantum event triggers, the universe branches. In one branch, the gun fires. In the other, it clicks. In the branch where the gun fires, the physicist's conscious experience terminates. In the branch where it clicks, the physicist's conscious experience continues. Both branches are real. But here is the asymmetry that changes everything. A conscious observer can only ever find themselves in a branch where their conscious experience continues, because finding yourself somewhere requires having a functioning experience to find. You cannot observe your own non-existence. A dead physicist is not a physicist who experiences being dead. They are simply absent. So from the subjective perspective of the physicist in the experiment, what is the inevitable experience? The gun clicks. Every time. The probability is still 50-50 in the objective, branching sense, but the physicist's thread of experience can only follow branches in which the physicist is still there to have a thread of experience. The branch where the gun fires is real. It contains a version of events where the physicist died, but that version contains nobody to experience it from the inside. Pull the trigger a second time. The universe branches again. Click. A third time. Click. A 10th time. A 100th time. From the outside, an observer watching would see a physicist who has survived a sequence of events that should have killed them dozens of times. Someone who, statistically, looks extraordinarily lucky. From the inside, the physicist experiences nothing unusual at all. They just keep hearing a click. Every time. Because every time, the only branch they can be in is the one where the click happened. This is not a trick of perception or a philosophical sleight of hand. It follows directly, mechanically, from two premises that are individually not controversial. First, that many worlds is correct, and all branches are equally real. And second, that a conscious observer can only observe the branch they exist in. If you accept both premises, the conclusion is not avoidable. The physicist survives, subjectively, every single trial. Not because they are protected, not because some principle of the universe values their life. The architecture of branching reality, combined with the requirement that experience requires an experiencer, filters them into survival automatically. Now extend this logic beyond a single afternoon with a gun. You are not conducting a quantum suicide experiment right now, but every moment of your existence is, in a physically precise sense, already a version of the same situation. Every second of your life, quantum events are occurring in your body, in the electrochemical processes of your neurons, in the molecular machinery of your cells, in the atoms of the air passing through your lungs. Most of these events have no consequence for your survival, but some of them, occasionally, rarely, at the margin, could branch into outcomes that are fatal. A cancerous mutation that happens or doesn't because of a quantum fluctuation in a DNA strand. A blood clot that forms or doesn't. A synapse that fires or misfires at a critical moment. At every one of those junctures, the universe branches. In some branches, the outcome is fatal. In others, it isn't. And under the same logic as the quantum gun, you are always, from your own perspective, in the branch where it wasn't. This is quantum immortality. Not immortality in the sense of being indestructible in a single timeline. Every branch where you die is real. Countless versions of you have already died, from the perspective of outside observers in those branches. But from your own subjective perspective, from the inside, from the thread of experience that you actually inhabit, you will always find yourself in a branch where you survived. The experience of death from the inside is not an experience. It is an absence. And your experience, by definition, can never be an absence. Taken to its logical endpoint, this means something staggering. Across the full branching structure of the universe, there is always a branch, no matter what, where you survive just a little bit longer. Not comfortably, not healthily. The branches that contain a very old version of you are exponentially rare, vanishingly unlikely from any outside perspective, representing a needle in an infinite haystack of branches where you died at various earlier points. But rare is not the same as non-existent. And your subjective experience will always, without exception, be located in one of those rare branches. You will age. You will become, in the surviving branches, someone whose survival looks increasingly improbable to everyone around them. But you will never, from the inside, experience the moment where it stops. The logical conclusion, pushed all the way, is deeply unsettling. The version of you that persists through all branching points doesn't persist into a pleasant eternity. It persists into a world where everyone you know has died in their own branches, where your own body has failed in every way short of the final one, where the survival has become something that looks, from outside any given branch, like a grotesque anomaly. Quantum immortality, if real, is not a gift. It is something stranger and more disturbing than that. In 1998, a cosmologist decided to put his name on these ideas in a published paper. That was not a small decision. Max Tegmark was 30 years old, working at the Institute for Advanced Study in Princeton, the same institution where Einstein had spent the last decades of his life, when he submitted a paper to the journal Foundations of Physics. The paper was titled, "The Interpretation of Quantum Mechanics, Many Worlds or Many Words." And it did something that most physicists considered professionally inadvisable. It took the quantum suicide argument seriously, in print, under a real name, as a genuine scientific question about the nature of reality. Tegmark's paper didn't just describe the thought experiment abstractly. He personalized it. He used himself as the hypothetical experimenter. He described what he would experience if many worlds is correct, and he pulled the trigger of a quantum gun, and what he would experience if Copenhagen is correct instead. This was a deliberate rhetorical choice, and he was explicit about why he made it. By putting himself in the scenario, by writing "I" instead of "a physicist," he was forcing the reader to confront the fact that this is not a question about abstract particles or hypothetical cats. It is a question about what happens to a conscious person, to you, to him, at the moment of a branching event involving their survival. He also, carefully and explicitly, stated why he would not actually conduct the experiment. The reason is not what you might expect. It is not that the experiment is dangerous or that he was afraid to die. It is that the experiment proves nothing to an outside observer and therefore proves nothing to science. If many worlds is correct and Tegmark survived 100 trials, an external observer would see exactly the same result they would see if Tegmark was simply lucky. There is no way, from outside, to distinguish a quantum immortal from a person who got lucky. The subjective certainty of the survivor, the fact that, from inside, the result feels inevitable, is invisible to anyone watching. And a result that is invisible to any observer other than the subject of the experiment is not a scientific result. It is, at best, a personal conviction. Science requires the ability to compare notes. If you're the only one who can observe the relevant data, your own continued existence, you have no science. You have a sample size of 1, and that sample is yourself. Tegmark put it directly. The experiment would be, he wrote, a purely private experiment. You would know if you survived. But you can't tell anyone else anything they couldn't already have concluded from pure statistics. The experiment is, in that sense, unfalsifiable, which doesn't make it wrong, but it does make it something other than an experiment in the ordinary sense of the word. The paper attracted attention. Not universal praise, far from it, but serious engagement from people who had never expected to see quantum suicide discussed in a peer-reviewed journal. Tegmark later reflected that he'd written it partly because he wanted to clarify his own thinking about many worlds, partly because he thought the thought experiment revealed something genuinely important about the difference between first-person and third-person perspectives in physics, and partly because nobody else was willing to say it out loud. He has since moved to MIT, where he runs a research group focused on the foundations of cosmology, and has become one of the most publicly visible advocates for taking many worlds seriously as a physical hypothesis rather than a philosophical curiosity. There is one more layer underneath the quantum suicide argument that makes the whole structure harder to dismiss than it first appears. The fact that you exist to read these words is not a neutral fact. It sounds like it should be neutral. Of course you exist, otherwise you couldn't be reading this. So what does your existence tell you? But the logic of observer selection, applied carefully, says it tells you something real. Think about it this way. Suppose the universe began in some initial state, and across all of time, the vast majority of possible versions of that universe contain no conscious observers at all. Most branches of the wave function, most configurations of matter and energy, produce nothing that thinks, nothing that asks questions, nothing that reads a sentence and wonders what it means. In those branches, there is nobody to notice that nobody is there. Now, which branches can you possibly find yourself in? Only the ones that contain a conscious observer. Not because those branches are more likely, maybe they're astronomically rare, but because branches without observers contain nobody to find themselves anywhere. This is called the observer selection effect, and it is the quiet engine running underneath all of quantum immortality. The simple fact of being conscious and asking a question is already a filter. It tells you that whatever universe you're in, it's one of the rare ones compatible with the existence of something like you. And the same filter applies locally, at every moment. Whatever branch you're in right now, it's a branch where you survived to this moment. The fact that you nearly died 3 years ago, or that certain molecular events in your body came within a hair of going fatally wrong, doesn't change that. You're here. That's not surprising, given that you're here, but it does mean that your continued existence is always, in a probabilistic sense, an outcome that was selected for by the simple fact of your being the one doing the observing. The anthropic principle, the name for this class of observer selection arguments, sounds like a tautology. Of course you find yourself in conditions compatible with your existence. What else would you expect? But the tautology has teeth, because it means that no matter how improbable your survival looks from any given external vantage point, your perspective will always be the perspective of the one who made it through. Always. Without exception. The alternative branches don't report in. And this is where the argument develops a weight that's hard to set down. Not because quantum immortality is obviously true, but because the objections to it are not as clean as they look. Most physicists who hear this argument for the first time reach immediately for the obvious response. Many worlds is probably wrong, so none of this applies. And that is a legitimate response, if it's well supported. But when you push on exactly why many worlds should be wrong, and what the alternative is, and whether that alternative actually solves the measurement problem, or just relocates the mystery, the dismissal starts to cost more than it seems. The objections are real. They are serious. Several of them point to problems with the many worlds interpretation that Everett himself never solved, that remain unresolved today, and that might genuinely be fatal to the whole framework. But they also create new problems of their own. Problems that look, from certain angles, just as strange as the one they were designed to escape. There is a physicist sitting in a laboratory at the University of California, Santa Barbara, sometime in the early 2000s, looking at data that will not cooperate with a beautiful idea. The team is measuring quantum coherence in biological molecules, specifically in a class of protein complexes involved in photosynthesis. The question they are trying to answer is whether quantum superposition can survive long enough inside a warm, wet, living system to actually do anything useful. Whether life, in other words, uses quantum mechanics in any meaningful way beyond the trivial fact that everything is made of atoms. The results are strange. Not in a good way, in a deeply inconvenient way. The coherence is there, briefly, spectacularly. Quantum superposition showing up inside a living molecule at room temperature, where almost nobody expected it. But it lasts for a fraction of a picosecond. A picosecond is 1/trillionth of a second, and then it's gone. Smeared into the thermal noise of a warm environment, dissolved by contact with the surrounding molecular bath. Every trace of quantum weirdness ironed out, before it could possibly influence anything at the scale of a brain, a body, a decision. This is decoherence, and it is the first serious scientific objection to quantum immortality. Not a philosophical quibble, but a physical fact about how the quantum world behaves inside warm, dense, complex systems like the human body. For a single electron in a vacuum, superposition can persist indefinitely. For an electron in your brain, surrounded by 37 trillion cells, each one a churning bath of thermal fluctuations and molecular collisions, the timescales are incomprehensibly short. We are talking about times far shorter than the timescales of any biological process. A nerve impulse takes milliseconds. Quantum coherence in a warm biological system lasts picoseconds or less. By the time any quantum event in your brain could possibly influence a neuron firing, it has already lost every trace of quantum character and become, for all measurable purposes, a classical event. What does this mean for quantum immortality? It means that the branching events that matter for your survival are not cleanly quantum in the way the thought experiment requires. The quantum gun works as a thought experiment because it posits a direct, clean link between a single quantum event and a macroscopic outcome. Atom decays, gun fires. But your body is not a quantum gun. The relationship between quantum events in your cells and your survival is mediated through layers of warm, noisy, decohering complexity that smear quantum branches into something that looks, at the macroscopic level, effectively classical. The branches are still there, in principle. Decoherence doesn't eliminate them from the wave function in the many worlds picture. But they become so entangled with the environment, so diffused across so many degrees of freedom, that the question of which branch you are in loses the clean meaning the thought experiment depends on. The researchers looking at that picosecond coherence data were not thinking about quantum immortality. They were thinking about photosynthesis. But what they were seeing is the same principle at work. Life happens too fast, too warm, too entangled with its surroundings for the quantum layer to reach up and touch the classical layer in the way quantum immortality requires. The bridge between the quantum event and the survivable outcome is a bridge that decoherence keeps dismantling before it can be crossed. And yet, the decoherence objection, as powerful as it is, doesn't quite close the door. Because decoherence is a practical limitation, not a metaphysical one, it tells you that quantum branches become impossible to distinguish from the outside, and that their influence on macroscopic biology becomes vanishingly small on most timescales. It does not tell you that the branches stop existing. In the many worlds picture, they are still there. Every branch still contains a version of the wave function. The quantum immortality argument doesn't require you to be able to tell which branch you're in from outside. It requires only that, from inside, you are always in a branch where you survived. Decoherence makes the thought experiment much less clean. It makes the practical implications far murkier. But it doesn't deliver a clean, logical refutation. It muddies the water without draining the pool. So you're left with decoherence, making the simple version of quantum immortality implausible as a lived human experience, while leaving the abstract structure of the argument technically intact, which is exactly the kind of result that keeps philosophers employed. But there is a second objection, and this one doesn't come from physics. It comes from asking a much more personal question. Even if quantum immortality works exactly as described, even if, across the branching structure of the wave function, there is always a thread of experience that survives, what exactly is doing the surviving? Consider what you are. Not philosophically, for the moment, but physically. You are a pattern. A specific arrangement of roughly 37 trillion cells, each one replacing most of its molecular components over years, each one part of a larger system that is constantly in flux. The atoms in your body are not the same atoms that were there 7 years ago. Most of them have been replaced through normal biological turnover. The neurons in your brain form new connections and lose old ones continuously. The you of 10 years ago and the you of today share a continuity of memory and psychological narrative, but they share only a partial overlap of physical substrate. This is already philosophically uncomfortable. Personal identity, even in ordinary life, is not a simple matter of tracking a single physical object through time. It is something more like tracking a pattern, a story that a physical process tells about itself as it continues. Now apply branching. At each quantum branching event, two versions of the pattern diverge. In most cases, they are nearly identical. The difference is at the level of a single molecule, and the downstream effects are negligible. But over time, those small divergences accumulate. The branch where a slightly different set of quantum events occurred in your brain last Tuesday has, by now, a slightly different pattern of neural connections, slightly different thoughts, slightly different decisions made in the last 72 hours. The two versions of you are still close enough to be effectively identical, but the gap doesn't stop growing. Push this out across decades. The branch of you that is, say, 140 years old, in whatever implausible state of survival that branch contains, has been diverging from you as you currently exist for more than a century of accumulated quantum differences. Every day, trillions of quantum events have pushed that branch's patterns slightly further from yours. The memories are there, presumably. The continuity of narrative is there. But the relationship between that ancient, surviving pattern and you, right now, is not obviously different in kind from the relationship between you and a distant cousin. You share a common ancestor. You diverged. There is a thought experiment in philosophy, much older than quantum mechanics, called the ship of Theseus. A ship has all its planks gradually replaced, one by one, until none of the original wood remains. Is it still the same ship? Most people feel intuitively that it is, because the process was gradual and continuous. But now imagine someone saved all the original planks and rebuilt the ship from them. Which one is the real ship of Theseus now? The quantum immortality version of this problem is more extreme. You don't have one ship that had its planks replaced. You have a tree of ships, each one diverging from the others at every moment, each one claiming the same continuous history, each one being, in their own branch, the one that kept surviving. The ship that is 400 years old in some improbable branch is not the ship you're standing on. It's a ship that once was the same ship, a very long time ago. Whether that distinction matters, whether identity is the kind of thing that can survive across that degree of divergence, is not a question physics can answer. I find this the most personally unsettling part of the whole argument. Not the thought of dying, but the thought of what not dying would actually mean. The branch where I survive to an impossibly old age is not me having a long life. It is a copy of me, made right now, kept alive across an eternity of branching events that keep accumulating differences, until whatever is left has only the faintest structural relationship to the person writing this sentence. That's not immortality. That's something that doesn't have a good name yet. In the summer of 1997, physicists and philosophers of physics gathered at a workshop at the University of Oxford to discuss the foundations of quantum mechanics. It was not a mainstream event by the standards of the field. Most working physicists at that point had, following the Copenhagen tradition, simply stopped asking foundational questions. Shut up and calculate, as the unofficial motto went. The people who showed up at Oxford were the ones who couldn't stop asking. David Deutsch was there. He had spent years developing a version of quantum computing that took many worlds entirely seriously as a physical framework. In his view, quantum computers derive their power from computations happening in parallel across multiple branches. And if you don't accept the reality of those branches, you don't really have an explanation for how quantum computing works. For Deutsch, many worlds wasn't a philosophical preference. It was the only interpretation that actually explained something. Also present were people deeply skeptical of many worlds, for reasons ranging from the mathematical to the practical to the visceral. The visceral objection came up more than once. Many worlds is, in the language of physicists, ontologically extravagant. It posits an extraordinary, literally uncountable number of real, physical branches of the universe, each one containing complete copies of every person, every planet, every galaxy, an infinite library of realities, all equally real, none of them communicating with any other. For some physicists, this felt like an obscene multiplication of entities, a theory that paid for its mathematical elegance with an infinite metaphysical debt. Occam's razor, they felt, should cut many worlds apart. You don't solve the measurement problem by making every possible outcome real. You solve it by explaining what actually happens. The problem nobody in that room had resolved, and nobody has resolved since, is that every alternative to many worlds has problems of its own that are at least as severe. The Copenhagen interpretation refuses to say what collapse actually is or where it happens. Hidden variable theories, Einstein's preferred escape route, have been largely ruled out by experiment in their simplest forms, and their more complex versions have their own extravagances. Objective collapse theories, which try to add collapse as a genuine physical process, require introducing new physics that has never been observed. Every door out of the measurement problem opens into a room with another locked door. There was no consensus at Oxford in 1997. There has been no consensus since. When surveys of physicists are conducted at conferences about which interpretation they favor, the results are fragmented, shifting, and frequently embarrassing to the field. Not because physicists are confused, but because the question is genuinely unresolved, and the honest answer is that nobody knows. The theory works. What it means is still up for debate. And this matters for quantum immortality directly, because quantum immortality is not a freestanding claim. It is a consequence of many worlds combined with the observer selection effect. If many worlds is wrong, or if it's right but decoherence makes the branching practically irrelevant to biological systems, or if personal identity doesn't survive branching in the way the argument requires, then quantum immortality collapses. It's a chain of dependencies, each link of which is contested, but the chain has never been cleanly broken. Every attempt to snap one link encounters the problem that the link is attached to questions that nobody has answered. Now, set aside whether quantum immortality is true. Suppose, for the sake of honesty, that it probably isn't. that the decoherence objection is fatal in practice, that the identity problem dissolves the argument, that many worlds itself is eventually superseded by a better theory that actually explains what happens during measurement. Suppose all of that is true, and quantum immortality is a beautiful, seductive, ultimately wrong idea that emerged from a beautiful, seductive, ultimately incomplete interpretation of quantum mechanics. It still leaves something behind. Because even if the specific mechanism fails, the type of question it asks does not. What is the relationship between physical process and subjective experience? Where exactly, in the branching or collapsing or evolving wave function, does the experience of being a particular person get located? If the physics is silent on which branch you inhabit, is there something the physics is missing? Or is there no you to locate in any branch except as a pattern that carries a story forward? And the question of which one is really you is simply the wrong question. These are not questions quantum mechanics invented. They are questions consciousness has been asking since humans first started asking anything. What quantum mechanics did, what Everett's stripped-down, career-ending, ultimately vindicated thesis did, was drag those questions into the domain of hard physics. It took the soft problem of identity and personal continuity and embedded it inside a mathematical framework that requires an answer. Not because the mathematics cares about consciousness, but because the mathematics, taken seriously, cannot be completed without one. There is an image that stays with me from all of this. Somewhere in the branching structure of the universe, in some branch, real under many worlds, real in the same sense that everything is real, there is an extraordinarily old version of you. Not a comfortable old, not a wise elder surrounded by family, something barely recognizable. A pattern that kept surviving by narrower and narrower margins through quantum events that, in all but a vanishingly rare set of branches, went the other way. A consciousness still running, attached to a body that has failed in every way short of the fatal one, in a world where everyone who knew you has been gone for longer than you can fully register. That version of you has not died, but they are not you either. Not in any sense that should comfort you. They are what you become when survival is the only thing the universe keeps selecting for, stripped of everything that made survival worth having. That image is not meant to frighten you. It is meant to make you feel, in a visceral way, what the quantum immortality argument actually implies when you stop treating it as an abstract physics puzzle and start treating it as a statement about experience. About what it means to be a conscious thing in a universe that may or may not care about the difference between one of you and 1,000 copies of you. About what we mean when we say that a person continues. The real legacy of this thought experiment is not a promise of survival. It is a question about what survival means. And that question, whether the many worlds exist or not, whether the wave function collapses or not, whether you will live forever in some branch or simply end as all things end, is one that physics opened and cannot close alone. Hugh Everett died at 51 and never saw his idea taken seriously. He reportedly told people close to him that he believed he would live on in branching universes, that in some branches he was still alive, still working, still thinking about the wave function. Whether he meant it literally or poetically, nobody recorded for certain. He died in his sleep, a heart attack, in his home in McLean, Virginia. No warning. Physics gave us the question. It didn't give us the answer. And maybe that's exactly right. Because the question is worth more than most of the comfortable answers we usually settle for. If this channel makes you think about the universe differently, subscribe. And if there's someone in your life who would lose sleep over a question like this one, the good kind of lost sleep, the kind that means something shifted. Share this video with them. It might be the most interesting thing they see this week.